Good afternoon and welcome again to the Communication and Signal Processing Seminar. Yes, so we are going to go marching along on Thursdays, 4 to 5, no more Friday morning ones. So I'm delighted that this week we have Dimitris Papailiopoulos.
Pretty good.
And before I introduce him, I'm going to have to thank first our Shelley Felcam and Catherine Goodwin, who've been behind the scenes helping to organize the seminar. So Dimitris is an assistant professor in the EC department at the University of Wisconsin-Madison. He's a faculty fellow at the Granger Institute for Engineering and a faculty affiliate at the Wisconsin Institute of Discovery. His research interests span machine learning, information theory, and distributed systems, with a current focus on efficient large-scale training algorithms and coding theoretic techniques for robust machine learning. Between 2014 and 2015, Dimitris was a postdoc researcher at UC Berkeley and a member of the AMP lab. Did you work with Kannan, I guess? Or, yeah.
Yeah. So I was working with Kannan and Ben Recht.
Okay. He earned his PhD in EC from UT Austin in 2014. He was under the supervision of Alex Dimitris, who was a speaker last time in the fall. In 2007, he received his EC diploma. In 2009, his MSc degree from the Technical University of Crete in Greece. Dimitris is a recipient of the NSF Career Award in 2019, two Sony Faculty Innovation Awards in 2019 and 2020, a joint IEEE ComSoc ITSoc Best Paper Award in 2020, an IEEE Signal Processing Society Young Author Best Paper Award in 2015, the Villas Associate Award in 2021, the Emil Steger Distinguished Teaching Award in 2021, and the Benjamin Smith Reynolds Award for Excellence in Teaching 2019. In 2018, he co-founded MLSys, a new conference that targets research at the intersection of machine learning and systems. And in 2018 and 2020, he was the program chair for that conference. And in 2019, he co-chaired the third Midwest Machine Learning Symposium. With that, I give the floor to Dimitris. Please take it.
Thank you, Vijay. Thank you for the introduction, and thank you for inviting me. So I will just turn my video off now, but I promise to turn it back on when the questions come at the end. So yeah, let me see. Let me just do the full screen thing now. This here. With that here, I can't see anybody, but if somebody can be muted, just say that you can see my slides. That'll be great.
Yeah, I can see your slides. Yeah.
All right, awesome. Yeah, so please, I welcome questions throughout this talk. We can have it be as interactive as you like. I enjoy questions. I'll try to speak no more than 50 minutes, but if I do, please stop me. So today I want to talk to you a little bit about the research that my group has been doing in the area of pruning. So pruning traditionally, you'll see that it's used in sparsifying models. But very recently, there's an interesting observation that kind of like boils down to this quote by Michelangelo. So Michelangelo said that every block of stone has a statue inside of it, and it's the task of the sculptor to discover it. So today we'll talk about the neural network equivalent of this, I think. So I kind of want to start with the theorem itself, right? So this is a result that we published at NeurIPS 2020. It was a spotlight paper. And I'll spoil for you the result, just so you can have it in mind. And I will try to explain why I think it's interesting. But I want to make sure that we're all on the same page. So there is a network of depth L and width D. It's a neural network. You give it inputs, it gives you outputs. And it's say has good performance for, I don't know, CIFAR10 or ImageNet or whatever your favorite data set is. So this is some labeling function that is represented by a neural network. What I promise to you is the following, that you can make this a little wider, and you can prune this to obtain a network that approximates the performance of the original one, the labeling performance of the original one. The main guarantee is that in terms of the depths, this is only a network that's twice as deep, and a log factor wider. So if you start with width D, this is only D log, basically D over epsilon, where epsilon is the approximation guarantee, and I will talk more about it. But kind of the point of this is that any network, I say trained here, but in fact, any neural network can be approximated by, or, you know, the function that it represents can be approximated by pruning one that's random and only a logarithmic factor wider. And again, the point here, I don't know if you folks can see my pointer, but the point is that the weights of this network, these are completely random. Okay, there's nothing trained here. And what I will promise to you is I can find a network inside here that approximates the performance of the original one. And this random, it can be basically anything that contains the dynamic range of the weights of the original network. So I just want to take a quick pause here to see.
So Dimitris, we can see your pointer. So yeah, go ahead. I mean, we can see the mouse move. Yeah. Okay,
excellent. Yeah. So I just want to take a pause here to see if there's any question. So this is a good time to see if there's any questions on this this part. So again, the promise is there is some neural network, whatever depth and width. I promise to you, if I make it log times wider, I can completely start from a random network, prune it down to approximate the performance or the function that the original network represents. That's the statement.
So So I guess should we think of this bigger network as sort of a distribution on the other?
It's not quite a distribution. That's a good question. So it's it's a basis somehow that contains a lot of things, among them a combination of weights that will result to the original network. But I don't know if I would call it a distribution quite. I mean, it is random, right? But and there's a lot of other things in it. So I guess in that sense, it is a distribution. But the point is that with high probability that neural network will be found inside this relatively small one. And I guess one point I want to make is that this statement is not surprising if I were to tell you the new network is exponentially wider than the original one, because just by sheer chance you could find the weights, right? But I think the key part here is that you only the log factor widening.
And in the central network that you're pruning, is the length of that network, the number of layers, twice the number of the original network layers?
Yeah, it's twice as deep, this probably is more an artifact of the analysis rather than it being a requirement. And you will kind of see why this is too as much. I'll show some parts of the proof, and I think it's going to become clear there.
And the pruned network that you have, which is approximating the original network, it will also be of twice the length, or are you pruning in the length dimension too?
Correct. No, yeah, I'm not pruning the length.
Okay, thank you.
So, I mean, your performance is in the output sense, it's good, right? I mean,
correct. So, yes, exactly. So you look at them as f of x, right? So f of x and f prime of x or whatever, and you say one function is epsilon close to the other one.
I see. So you're only approximating the higher order function, the abstract function, but the architecture of the models can be different.
So the architecture is the same in the sense that they will both use the same ReLU functions and all that. But the actual, whether it's wider or deeper, that will be different. But in terms of components, it's like, they're going to be of the same kind.
Okay, thank you.
And so should we, I mean, I guess instead of going down from the bigger network to the smaller network, what does this say about the bigger network's expressibility, as in?
Yeah, that's a good question. So basically, and that's actually a very deep question. So we'll come back to this in a little bit, but essentially what this will say is that, in fact, not just the target network can be approximated by pruning, any network of that size can be approximated by pruning this larger network. So in some sense, this larger network, you can think of it as a, from that you can construct an epsilon net of the smaller size network. So if you give me that big block of stone in the middle, I can prune it out to get any network that is of these dimensions, or for any, with regards to any output that this kind of network, gives, right? So take f, let's say if it is the class of functions approximated by this network. The promise is if you give me this block of stone, I can carve it down to approximate any function from here. Does it make sense?
Yeah.
All right, awesome. Any other questions?
Is this, so, I mean, are the width and the length somewhat the best you can do, or can you go even?
So yeah, so that's a great question. So we have some lower bounds, and I'll talk about them at the end if there's time. The log 1 over epsilon is sort of tight. You can't get rid of it. The log DL, maybe you can get a better dependence, but the dependence on the error is definitely the best you can get. In terms of depth, the two-factor, in fact, I don't think it's needed. You can probably get rid of it. All right. Is there anything else? Yeah.
Does this result apply to any network architecture? For example, different activation function, or maybe convolutional network, or even self-attention modules?
This is a very good question. So the theorem, the way that I will present it, is for fully connected ReLU networks. However, it's quite easy to generalize to convolutional networks. It's not in the paper, it's sort of an easy observation. In fact, any function that is, ReLUs, sigmoids, tanates functions. So these functions can still, these theorems, you can kind of like rederive them. So I will explain at the end how probably this can happen. But I would say that this is reasonably general in that sense. So, attention, convolution, transformers, other activations, you can basically rederive those results for most of these architectural components.
I see. Thank you.
All right, great. All right, so let's see why this. I'll try to convince you that this is interesting now. Okay, but this is the main theorem. So I'll take a step back, and I want to tell you a little bit about network pruning. And traditionally, network pruning, and this dates back to the 80s. LeCun had a paper called the Optimal Brain Damage, I think, and then Babak had another paper the early 80s. And basically, the point of those papers is to say, look, you start with a dense architecture. Maybe it's a ResNet, maybe it's a LeNet, maybe whatever your favorite architecture. What I would like to do is get another one that's thinned down, one that is sparsified in some domain, in this case, the domain of the weights. And the goal of that, or the hope, is that by doing this, you will have a network that takes less energy, compute, and memory when you do inference or training or whatever. And potentially, maybe it's more interpretable if it's sparser. In any case, sparsity is a desirable property, and that's why pruning has been traditionally used. That people, the literature that does pruning, the network pruning literature, the way that the algorithms usually look as follows. You start with your architecture, again, whatever that architecture is, convolutional nets, ResNets, or whatever. You randomly initialize them with weights, real weights, and then you fully train the network. Right? So you train the network with SGD until you get full accuracy, and then you stop. And then you say, look, I want to kill some of those weights. So you start pruning some of those weights, but the result of that pruning, no matter what the metric of pruning is or how you do it, is that this will result in some accuracy loss. The way to mitigate this accuracy loss is go back and retrain those surviving weights, potentially maybe some of the dead weights as well. But kind of the idea is that you retrain to regain anything that was lost due to pruning, and then continue by pruning even more. So this is, I would say, the biggest fraction of work on network pruning, without, of course, characterizing every single paper, but a big fraction of network pruning uses this pruning and retraining idea that arguably may be a little bit expensive because you have to repeat the cycle several times. And because of the fact that there's a bunch of parameters, it may also be hard to tune. So there has been, for quite a while, the question of whether you can bypass this pruning and retraining. And I will explain how, how this sort of was partially resolved in a little bit. But before I go to the next slide, I just want to make sure that everybody's on board with just the general idea of pruning and why traditionally pruning is used. All right, great. So here's the kind of like, the exciting part of sort of the history of pruning. So there's been a lot of work in the 80s, and there's been sort of rekindling of the interest in the early 2000s with a couple of papers, or a couple hundred of papers, I should say. A couple of years ago, in 2019, there was something called the lottery ticket hypothesis that was presented by Jonathan Frankel and Mike Carbin from MIT at iClear 2019, which actually won the Best Paper Award. So what they said in that paper, and what basically the lottery ticket hypothesis postulates, is the following. What Jonathan and Mike promise is that at initialization, so you get your network and you initialize it, there is a lottery to be won. So if you win the lottery, what will happen is you will not have to do this pruning and retraining thing. You will only have to train once. The lottery ticket hypothesis literally says that at initialization, without doing anything, initialize your weights at random. At that initialization, there exists sparse subnetworks that can be trained just once to full accuracy without having to go back and close the cycle and just kind of like repeat this retraining thing. So you prune once at initialization, and then you train once, and that's it. Okay, so that's the idea of, like, winning the lottery. And of course, the question is, is it expensive, right? But I guess I just want to make sure that everybody's on board with the lottery ticket hypothesis. If you have any questions, I'll be happy to take them now. Just take, maybe 5-second pause here. All right, so again, the hypothesis says that there exist sparse networks at initialization that can be trained to full accuracy. Essentially, Frankel and Karpin showed that this hypothesis seems to be true for the networks and the experiments that they run. And this is sort of a big deal because you can kind of avoid the pruning and retraining, right? So if the cost of winning that lottery is not that high, computationally speaking, then that's going to be really cool. You won't have to do this pruning and retraining. And of course, the question is, what is the cost of winning the lottery? And there's been a lot of papers in kind of like explaining how you can obtain those sparse subnetworks that have the property that they only require to be trained just once. Sort of the magic of this paper, let's say, is that the authors prove that the lottery tickets are much better. By lottery, when we say lottery tickets, we mean those sparse subnetworks. Those sparse subnetworks are much better than random subnetworks. Someone may ask, okay, what if I were to just randomly pick a set of edges and just train those edges, right? So what they prove is basically, if you were to do this, if you were to train a random network, a random sparse subnetwork, this would have accuracy that would be significantly worse than that of the lottery ticket network. So there is something in this specially, special lottery ticket. So there are, they're definitely better than random sparse subnetworks. The other interesting thing is that sort of the initial weights kind of matter as well. So that is to say, you give me your lottery ticket, your sparse subnetwork, and I resample its weights. So I don't do anything with the zero weights. I resample the sparse, the non-zero weights. And what happens is that this network actually starts becoming random again. So there is sort of like something to be said about the weights as well. So both the architecture and the weights, the combination of the two is what makes those lottery tickets sort of special. And there's been a lot of work in this literature. I think the paper has like 500 citations and whatever, but the point is that it sparked a lot of intellectual interest in understanding the geometry and the algorithmic aspects of lottery tickets. But again, I want to take a little pause here to see if this makes sense. And if you have any questions about the lottery ticket hypothesis, I'm happy to take them at this point.
So, I guess the claim is you still have to train at least once the short.
Yeah.
Okay.
But I guess maybe the main point is that you don't have to repeat this cycle of training and repruning and retraining. So that's kind of the main benefit of those lottery tickets. But you do have to train them once.
But it's also you stop soon, right? It's not the early stopping is what you do.
There's no early stopping. No, you train it to full accuracy, and it may take as many epochs as the normal training.
Thank you.
Yep. All right. So I'm not here to tell you more about the lottery ticket hypothesis. I'm here to tell you something I think maybe more interesting even. So along this literature, there was a really cool paper by Ramanujan and Warsman at University of Washington in Seattle. And the title was "What is hidden in a randomly weighted neural network?" And what these guys proved experimentally is something very striking. And I will refer to this phenomenon as the strong lottery ticket hypothesis. And I will explain what they do in this paper. The strong lottery ticket hypothesis is a little bit different. It doesn't talk at all about training. It talks just about pruning. So the strong LTH says that pruning is all you need. Give me a network that's the same architecture as before, but maybe you make it a little wider. What they find is that state-of-the-art accuracy networks simply reside, they simply live within random wider neural networks. So you randomly initialize your network and you just prune, you cut weights, you kill off weights, and that new network has the same performance as the slightly less wide, fully trained dense network. Okay, so now this is not about sparsity. This is to say that you can create networks that are very, very accurate as state-of-the-art networks, but you can do this just by pruning. Okay, so you just kill off weights. The only computational thing you're allowed to do on the network is zero out a weight. You're not allowed to play with the weight, and you're not allowed to change it like you would do with SGD. You just either maintain a weight or you don't. So simply by pruning, you're able to create a structure, a network that's very, very accurate. So I just want to take a little pause just to make sure that this strong lottery ticket hypothesis makes sense to you.
So for CNNs, are we throwing out entire filters at a time, or just one coefficient filter, or is this only for fully connected networks?
Yeah, this is a great question. So for CNNs, there's two things you can do. Either you can throw individual weights of the filter, or you can throw entire filters. And that's what people call structured pruning, where you just throw away the entire thing. But you can do either. Yeah, that's a good question.
Thanks.
I have a similar question here. So does the pruning method matter here? So for the strong lottery ticket hypothesis.
Yeah, so that's a good question. So the algorithmic aspects are still vastly uncovered. So what is a good pruning algorithm is unclear. I will tell you what these guys are using. They use something that's almost like doing SGD on the pruning mask. So they don't tune the weights, they tune the sort of something else. I'll go back to that. But the algorithm itself is very important, right? It's kind of like the most important thing probably here. The question of how, what's the right way to do it, we still don't know. And I think this is one of the biggest open problems in this area, which is also very interesting. So I'll come back to this algorithmic question in a little bit.
Okay.
I have a quick question about the structured pruning you mentioned. Is it understood what type of structures still satisfy what you have here?
Yeah, so you can prune activations, you can prune convolutional filters, but the way what is better is unclear, because for example, if I were to just prune full activations, I'm throwing away too much, right? If I were to prune individual weights, I'm pruning, the resolution of the pruning is much higher, but then the algorithm may take more time. So it's not clear what the right way forward is. There's kind of like a benefit of pruning too many things, or large components, because you won't require too many iterations, but at the same time you may lose some accuracy by doing that. So it's not clearly understood. I guess that's the short answer. We don't know what the right way is.
There's also architectural dependence for some forms of unstructured pruning. They can mess up actual implementation on given architectures that are regular.
Correct. And in fact, you can if you overdo it, maybe you prune an entire layer and then the network output's always zero, right? So there's also that. But yeah, it's all these things you kind of have to keep in mind while you do the pruning. That's a very good observation. All right, awesome. So here's what I do in this paper. So they say, I'm going to have an algorithm that kind of looks like stochastic gradient, but it's a stochastic gradient on the pruning mask. For every edge, I will maintain a survival score, okay? If the survival score is high, I will keep the edge. If the survival score of that edge is low, I will kill the edge or the respective weight. The way that I update the scores is by looking by how much is a particular edge aligned with the current gradient that I'm computing on this network. So it's like, you think of it as a normal network. You compute the gradient of it, and you look at the coordinate, and you say, okay, is this coordinate aligned with the coordinate of the gradient? If the answer is yes, you update positively the score. If the answer is no, you decrease the survival score. So that's roughly the algorithm. But the point is that at inference, when you use the network, you use the pruning mask that tells you, these are the survival scores, keep the top K% at every layer, just go with those. And you only use the actual original weights. You don't tune the weights at all. Okay, so this is roughly the algorithm. And what they basically prune, so this is kind of like the accuracy that you can get. This is a bunch of smaller convolutional networks. These straight lines are the accuracy of the original dense network. And these balls, these inverted balls, are basically the accuracy of the prune network. And for this particular algorithm, they see that they get state of the art roughly at 50% of the weights. Okay, so by keeping 50% of the weights, which if you think about it, it's kind of like the regime where you get the maximum expressivity, right? So when I have like n over 2 of the weights alive, I have n choose n over 2 potential networks to choose from. Right at that range of sparsity, at 50% sparsity, they're able to match the performance of the fully dense network. Now, the crazy thing, and I still find this incredibly mind-blowing, is that they're not tuning weights at all. Okay, they still use a back propagation kind of an algorithm, but they're not doing anything to the weights apart from like either killing or letting them be. And when I read this paper, I was like, okay, this is just absolutely insane. And is this generally true, or is it because, in their case, they were using convolutional networks and ResNets, and it was on CFAR10, maybe the data set and the model themselves actually just, this is just a side effect of all of those things. I really want to understand if more generally you could approximate a target neural network by pruning, a larger network. And if you think about it, so if you spend like, maybe a few seconds here, you'll realize that, this question has a trivial answer, has a trivial resounding answer that yes, you can obviously always prune a larger network to approximate the target neural network if you do not constrain the amount of over-parameterization. If you tell me, for example, I start with a ResNet 50, but I give you a ResNet that's like 5 billion times wider, just by sheer chance, inside this, gargantuan network, I can find the weights of the original one, right? So I can definitely do this if you don't constrain the over-parameterization. So the question is not interesting, if you don't constrain how larger is the network that you're going to prune, right? So that's kind of like the important constraint that makes this problem interesting and challenging. So let me take another pause here just to see whether this makes sense to you. All right, awesome.
I mean, I guess you shouldn't have, to make the problem interesting, it has to be a small enough network that you prove, right? I mean, not too
exactly.
large.
Exactly right. Exactly right. Ideally, not much larger than the original one. And the reason for that is, in this paper, in the Ramanujan paper, what they basically show is that if you want to approximate the accuracy of ResNet 34, a fully trained ResNet 34 on CFAR10 or ImageNet, you can start with a network that is a little bit wider and a little bit deeper. And the factor was maybe the overall number of parameters of the bigger network was maybe like 2 times more parameters, something like that. So with twice as many parameters, they were able to say there's no need to train, just prune that thing and it will be accurate. And they only were using, the other thing I want to note is that they don't have access to the ResNet 34. They only have access to the labeled examples, right? But kind of like the point is that the requirement on the extra whatever amount of parameters that you need was not that big. So that's kind of like the regime that you want to play at.
I'm wondering if the initialization strategy matter here, because for example,
question. Yep, very good question. So it does play a significant role. So I'll come back to this, but the initialization plays a role. Okay,
so you need a specific initialization strategy here.
So here it's Gaussian. There is no, they don't play any weird tricks. It's just Gaussian. But whether you choose Gaussian or uniform or Laplace or whatever you want, this will actually impact the performance of the pruning algorithm. All right, so here at this point, you should be wondering whether you can learn stuff by pruning. And I think the answer to that is yes. I guess that's also the title of the talk. But let's see at least, from an existence point of view, what we can say. So we started thinking about this problem. It was NeurIPS back when we had actual conferences. This was at NeurIPS 2019 at Vancouver. And we're having a nice lunch with Kostis Daskalakis and Alex Dimakis at Vancouver, and we're discussing about this paper, the experimental paper, kind of like thinking, brainstorming about it, but it didn't go anywhere. And I was sort of like, I was sitting on this problem for a little while. I wasn't doing anything, and if you do this, if there's a problem that looks like super interesting, and there is probably a solution, Ohad Samir and his group are probably going to write a paper proving what you want to prove. So you have to act fast. So anyway, so what Aaron and Gilad from Charles Schwartz and Ohad Samir's group proved is that basically this strong lottery ticket hypothesis is true if you allow large overparameterization. So the result was the following. If you allow the random network to be a polynomial factor wider than the original one, then you can prune it to get a network that is, you can prune to get a network that has the performance of the original one, okay? What is the overparameterization? D to the power of 4, D is the width, L to the power of 2, L is the length or the depth of the network, and epsilon squared, epsilon is the error of the approximation between the pruned network and the original one. And arguably, I think this is still a very interesting bound because it's not exponential, right? So if it was exponential, you'd say, okay, it's trivial, but you can still do it with polynomial overparameterization. And kind of like the way that the proof, of course, it's a long paper. There's many components to the proof, but the main idea of the proof is that this is sort of the overparameterization you need so that there's enough weights in this much wider network to individually approximate the weights of the original network. Okay, so if there's enough weights, then you can prune it to find the weights of any network you like. How much larger do you need that to be if you were to sort of prune it in that way? This is the answer, kind of like this polynomial factor. And I think this is a great paper, and in fact, this is what motivated us to look even more into this problem. However, this result is not comparable with the findings of the experimental paper that were only pruning a network that was like 2-3 times bigger than the original one that they were trying to approximate, right? So the question is whether this factor of 2 difference here and this polynomial factor of difference here, whether maybe this is maybe what Ramanujan observed was just an artifact of I don't know CFAR10 and resonance, right? So that's the thing that we're trying to understand. But I just want to take another little pause here to see if there's any questions on the Malak paper or how it relates to the findings with Ramanujan.
I have a question. Does the random number generator matter at all? Since randomness is a finite resource, and when you're generating networks this large with random initializations, does that matter at all?
So that's a good question. So the assumption here is you would use the same random generator that if you were to run SGD, you would still have to start with a random network. So the assumption is you would use the same resources. Now, in terms of the particular theorems, we assume access to perfect random generators and like infinite precision and stuff like that. But of course, in reality, these things will matter, and in fact, depending on the number generator you have, the performance of pruning on these networks will potentially change dramatically.
I have a quick question on the problem setup. The original network you have, are there any assumptions on the network, or is it any network?
Yeah, so in this paper by Malak et al., and I guess I would like to note again that this is an existence result saying that good pruned networks exist. The assumption is you start with a fully connected ReLU network. So in this case, they focus on fully connected. And the activations are ReLU. But again, generally speaking, most of these theorems can be applied to more general architectures. But in terms of the data, for example, there's no assumption. Like this is a universal type of approximation for any data point, like any input-output pair. This approximation will be true. I don't know if this answers.
Can I just follow up on that? If you think about something like a UNet that has a lot of downsampling and upsampling, pooling and the like, it's not obvious to me how you would make it, so much wider or deeper. What's the net?
So again, is your question about whether this would apply to more complicated networks?
Yeah.
So experimentally, we know that this is the case. right?
Okay.
So the Malak et al. Paper, they use actual real ResNets, right? So these have they have max pooling, they have convolutional layers, they have fully connected layers. So it is possible. So it's not it's definitely not an algorithmic question of whether it's possible to implement this, because they already did it for sure. From the theoretical perspective, my answer, to my hand wavy answer at this point is that you can handle most of those. Maybe there are some things you can handle, but I wouldn't know what those are. But I wouldn't bet my life on it that they're probably there are things that you may not be able to approximate, but all the interesting stuff, it seems that you can.
Thanks.
Yep.
If I remember it correctly, the strong logarithmic hypothesis was for classification tasks only, right? So
this is a good question. So the paper by Malak et al. Is a regression. Basically, you approximate. It's basically a norm-bounded approximation. If you think of the original network and the pruned network as functions, it's approximations. It's an approximation that says f of x minus f of x prime are going to be less than epsilon. So that's kind of the result you get. So you can think of it as a regression, but this translates to classification results as well. In fact, the classification problem is a little easier than the regression in this case. But my short answer is you can handle both regression and classification.
Okay, thank you.
All right, awesome. So, okay, so I guess I kind of like explained how this works, but I just want to go back to it. So let's say you have a one weight, it's the most important neural network. It's one weight, it's a multiplier. You give it x, it outputs wx. I would like to approximate it. The idea of Malak et al. Is the following. I will over-parameterize that. I will be using this diamond structure. This is kind of like not exactly what's used, but it's useful for highlighting the idea. This diamond structure in the middle layer, just linear. There's no ReLU anything. Just, you give it x1, it spits out x1. And here what happens is you combine the layers, right? So basically whatever comes here is multiplied by xi. And whatever comes out from here, you just get the sum of this. Again, this is not, they generalize to ReLUs, but it's a good sort of little network to play with. Anyway, so they say, look, I will have this layer to be random. Okay, this layer for now is going to be a combining layer. And if I wanted to say, find the weight that's close to the original weight, and just keep that. All right. So this is what they do. Say, okay, find one of those xi's, and I want to make sure that one of those xi's is close to w. Right. So this is kind of like the main idea of the proof. Much more complicated than this, but I would say kind of like the core essence of their theorem. And the point is that if you would like to do this, if you would like to go down that path of kind of like approximating every weight by one of the weights of the random network, you stumble upon this polynomial barrier where you need 1/epsilon samples to get epsilon close to your target. You can't override this. This is just kind of like fundamental, right? So that's kind of the reason why essentially they get this polynomial over-parameterization in 1/epsilon. If you have to generalize this to arbitrary size of layers, you get the poly DL factors that appear there. But mainly, this is the reason why you get this dependence, and it is pretty much unavoidable. Does that make sense to you? So again, this is not exactly what they use in practice, but it's good as a sort of a little teaching gadget just to see what happens in their theorem. But I just want to make sure that this makes sense. So
Dimitri,
the question is,
yes, I have a question.
Yeah.
So, I mean, if we follow this idea and then we double that, now we have a slightly more complicated one, then we'll get exponential complexity. So the argument doesn't go through. At least I don't see it. There must be something more.
Yes. So there is something more. So the interesting thing is, like, if you go layer by layer, the error is not multiplicative somehow. It's kind of additive. So this does not explode exponentially. It is only going to be polynomial in 1/epsilon and the depth and the width. The way that you prove this, it's a little bit clearly, more involved than just that. But there's no, you won't get hit by an exponential by using this argument.
Okay. All right. Thanks.
So if you were to just say, look, I want to apply it on a weight by weight thing, you would get, 1/epsilon to the power of the weights, right? So you wouldn't be able to avoid this. But there is a little bit, if you push symbols a little bit around and you work with the fact that these layers are actually combining stuff, that actually helps you avoid this 1 over epsilon business. I mean, 1 over epsilon to the power of the number of the weights business. But yeah, that's a good point. This could be kind of the first the first order of approximation would say, okay, let's just do this for every weight, and then as you say, that's exactly the wall that you will hit. But you can improve it polynomial, and that's precisely why this theorem is not trivial.
Good, thanks.
All right, so yeah.
Sorry. So here, when we do the pruning, we don't look at the value of the initial weights, the random initial weights.
Yeah, you look at the value of the initial weight. So again, this is this is an algorithmic proof of existence that requires you access to the network, right? At the end of the day, you will just say networks exist, and you're giving Oracle access to, you're given access to everything, right? So you're kind of like an powerful, you know everything in this case. In practice, of course, you won't be given access to the true network. You will be only given access to labeled, input-output pairs.
I see. So, but basically, what I'm asking is, so when we do the pruning here, on the right-hand side, we just randomly pick one edge, or we need to. Yeah. Okay, so I see. So we don't look at the value of, for example, x1, x2, something like this.
Yeah. So you basically look individually at the values, and you're like, okay, I'll just pick the one that's closest. So that's how they do it. And you ask, okay, if I do that, if I look at literally the closest distance between xi and w, how close do I get? And the answer is, if you have n samples, you can get 1 over n close to the original weight.
I see. Okay, thank you.
All right, awesome. So so the result that we have, basically, I guess I gave it in the beginning, gives an exponential improvement to the overparameterization. Instead of multiplying the width by a poly factor, we multiply it only by a logarithmic factor, and also the error appears inside the logarithm. And I want to explain to you how we get this result. So here's the idea. So again, the Malak et al. Paper says find the closest weight, but this misses out on an important opportunity, which is this combining layer here, right? So you have this layer that adds up stuff, and you might say, well, what if I were to select a subset of those weights? Maybe that would give me something more. And this is basically the idea that we try to understand here. So let's say that, again, you want to approximate a weight. You have this random structure. You have random weights on the left-hand side. You have ones on the right-hand side. These activations are just like linear activations, nothing fancy. And what if I were to say, look, I don't want you to give me the closest number to W, combine things, because this is what this layer, the output layer is a combination layer, right? So I can use this computationally to my advantage. I will let you combine stuff. So pick a subset and choose the best subset, right? So this is, in fact, the subset sum problem. So in this case, pruning would be to find the best subset sum that approximates the target. And by doing that, you now will have to ask, okay, what's the sort of the sample complexity? Or, if I wanted error epsilon in the approximation here, right? So the target weight T or W, with regards to how close can I get if I were to add things up or add these random variables up, how much can I improve? And here comes this amazing paper by Luker in 1998. So what Luker proves is basically exactly what we want. So here's what he says. Give me any random variable. In that case, let's say that they are IID between -1 and 1. What I can promise you is that you can approximate anything between -half and half within epsilon by only generating, I should say, a logarithmic number of those random variables. So again, every number in any range of numbers you like can be approximating by sampling log 1 over epsilon random numbers in a range that's twice as large as that, and by picking a subset of those, okay? So in some way, the subset span, if you want to think about it as such, of a set of numbers is much more expressive than just picking a single one of them. In fact, it's exponentially more expressive. With log 1 over epsilon random numbers, you can approximate anything in this continuous range of numbers within epsilon. Okay, so this is what Luker proves in 1998, which is sort of what we need, but not quite. And I will go into this in a little bit, but I just want to make sure that this theorem makes sense to you. All right, so if you were to take this theorem and draw it in a picture, this literally says the following. I have a vector, I have a target weight W. Instead of having that, I can have this diamond structure, which has random weights on the left. These are, uniform or Gaussian or whatever you want. On the right-hand side, I have, ones. I select a subset of those ones. The best subset is going to be epsilon close to the original weight, okay? So that's what the visual version of the pruning of, the theorem by Lukier says. But the problem here is that this is not quite what we want, right? So we want to transform this linear network into a ReLU network. And we want the weights not to be, random here and one here. We want everything to be random, right? That's what people actually use in, Ramanujan et al. Was using completely random networks. So there's a very simple observation. A single weight can be trivially be written as a sum of two ReLU functions. So a ReLU activation, again, is basically, it gives you the input. So if input is x, it gives you x if x is positive. It gives you 0 if x is not positive. And you can break a weight, a single weight network, into two little ReLU activations. And what you can actually do now, you can generalize Lukier's theorem into a theorem about ReLU subnetworks. So basically, what I can prove to you is I can make, I can approximate this blue part by pruning this larger ReLU now network that has random weights on the left and random weights on the right. And I can do this for this magenta part as well. I can do the same trick. And kind of like the point is that Lukier's theorem actually still holds as long as the product distribution between those two weights contains essentially the dynamic range of the weights that you're interested in, and essentially can be applied to ReLU activations. So that's sort of the way that we generalize Lukier's theorem to apply it and get kind of like the theorem that we want for ReLU activations. And now this is a node network, but it is a fully connected ReLU network. This is how you approximate the weight, and this seems wasteful, but the interesting thing is that the width of that network is log 1 over epsilon. So you need log 1 over epsilon of weights, and then you can prune them down to basically approximate the original weight. And this is where the factor of 2 comes in, because you kind of like you approximate W with pruning this sort of 2-layer network. So you can generalize this. So basically what I told you is how to approximate Wx. Similarly, you can approximate W transpose X, which is a linear function. And you can also kind of like generalize this to get an approximation for W transpose X. So basically what you can promise is, you can approximate W transpose X by pruning a large ReLU network that's fully connected. And of course you have to apply the activations on that, and you have to do this for every single layer. And what is left for us to do is basically take some standard operator norm bounds for each layer. And at the end of the day, we get an approximation that says that for any input, so we assume that the inputs are bounded, but this is not really important, but for any input, the function f of x can be approximated by a pruned network. So here, M are the weight matrices, random weight matrices. S are basically 0, 1 matrices that amount for pruning to that network. But the point is, by pruning this network, I can get epsilon close to fx for every x that is norm bounded. Okay, so that's kind of like the general theorem that we prove. And again, the point is that the size of these matrices is only logarithmic wider than the size of the matrices that are used to represent f of x. Do we have any question on this part now? Okay. So I only have 2 minutes left, so I won't go into the lower bound. There's a simple lower bound that uses packing to prove that the log 1 over epsilon is tight for our result. But again, I just want to conclude with a theorem which says that not your favorite neural network, but anything that is of, in this case, depth L and width D, can be approximating by chiseling down, by pruning down this big block of stone here. And this is sort of a uniform approximation result. For any input and any network you like, I can approximate it down by pruning a single random network. I only need a single random network to approximate everything in this function class. And I can do this simply by pruning. And again, I want to stress out that this is an existential result. I did not give you, the pruning algorithm I gave you is not practical because it requires access to the network, right? So this is not the pruning algorithm. This is just to establish that good prunings exist, okay? Just want to take another pause to make sure that sort of this now makes sense again. Vijay, just want to check. So how are we doing with time? Just I don't want to go over time.
No, you're good. You're doing very well. Yeah.
Okay. So I have an experiment, but just for the purpose, I will skip the experiment. For the purpose of the discussion, I just want to tell you about open problems that I think are interesting. So I'm totally fascinated by this area. Most of the people in my group are actually working on this now, and we were not working on this a year ago. So this is kind of like a new focus of our group. The one thing that we've been working hard at is to try and understand to what extent is pruning powerful and what do you actually need to get these results. So for example, we've been looking at the question of like, instead of like starting with a network that has random weights, what if I were to tell you, look, I'm starting with a network that only has plus minus one weights, right? You don't even get weights, basically, you just get signs, right? If you were to have such a network and you were allowed to prune it, just making some of them zero, could you get any of those approximation results? So that was an open question up to a month ago, but I think we've basically almost proved that when you care about classification tasks, you in fact can prune binary networks to get the same results as before. Basically, pruning logarithmically bigger binary networks is as good as training dense real networks, which I think is pretty interesting. However, it's still not quite close. Like we need, in this case, both the depth and the width to be a log factor bigger. And it only works for ReLU activations. It doesn't work for other activations so far. So there's a lot still to be done here. And we don't have, we have some algorithms that we're working with, but nothing that works very well yet. But this idea of pruning binary nets, I think it's really, really interesting, at least to me. And we're trying to understand a little bit more. But I just want to see if anybody has any questions so far.
So for here, are we starting with a binary net or starting with a dense net?
You start with a dense network. So this is like a dense, fully connected network in this case, or ResNet or whatever you want. And every weight is randomly initialized to be plus or minus one. There's not even scaling, just like literally plus minus one.
I see. So you want to prove that the strong non-trivial ticket hypothesis also holds for binary networks.
Yep.
I see.
So the other two things that I'm really interested in is the geometry and the algorithmic aspects of the LTH, so the strong LTHs. And the geometry is actually very interesting. So let's say, for example, I have two classes, whatever, cats and dogs, whatever. And think of now just like a single layer, right? So just a single neural network, a single layer neural network. And let's say I have a bunch of random activations. So like an activation is a hyperplane in this case, right? So everything that falls left in the hyperplane is going to be plus one. Everything is going to be right. It's going to be minus one. So you get a bunch of those random hyperplanes, okay? Now the act of pruning, if I were to prune activations, amounts to slowly removing hyperplanes in such a way that at the end, I get a classifier that correctly classifies the two classes. And there's actually a very rich literature in computational geometry about properties of arrangements of hyperplanes and random hyperplanes and how you can construct whatever a bunch of different cells that can do whatever you want them to do. And I think there's a lot of interesting sort of combinatorial geometry, computational geometry questions here that we've started looking at. The last open question that I think is probably the hardest is whether we can get pruning algorithms that are provable. So, for example, that algorithm that Ramanujan et al. Is using, it seems like a reasonable algorithm, but I would not necessarily call it maybe the most mathematically principled, right? So, SGD, we don't know how to prove things about it, but arguably it's a mathematically principled algorithm. You sample data points, you take a gradient direction for their losses, you get a new model. What's more natural than that, right? Sometimes we can prove things about it. For example, for some case of whatever, data generating distributions. But for pruning, this kind of like natural sort of mathematically principled algorithm doesn't exist. Like things that we have so far, they look more like heuristics rather than principled algorithms. And this is something that we've been trying to understand a little bit more, like whether we can get some more principled algorithms for pruning, and whether in fact we can prove something about those pruning algorithms for some very simple, maybe linearly separable problems, right? I think what would be really cool is to also get, there's so much work on combinatorial optimization and so many algorithms on combinatorial optimization, and I'm very interested to understand a little bit more what their role is in pruning, and whether maybe at the end of the day you can replace backpropagation and SGD with pruning algorithms. So that kind of like would be the pipe dream, but I don't know if this could be feasible. So I would like to conclude and open up for questions, but basically, this work is mostly about trying to understand whether pruning can be used for learning functions. We prove that if you allow a log D over-parameterization, then you can basically get an existence result of good pruned networks. And there's a lot of interesting open problems of, I would say the most interesting, whether, you can come up with neurally plausible pruning algorithms that do not use gradients and are faster than traditional backpropagation training. The answer to this question may as well be no, but I think it's a reasonable endeavor. And I will just close with, again, the quote by Michelangelo that, every block of stone has a neural network inside of it, and it's the, it's the task of the, the machine learning researcher to discover it. But yeah, so that's all from me, and I'll be happy to take any questions now. Let me just stop sharing my screen.
So Dimitris, yeah. So let me just share my slides a little bit. Just it's not.
Yep.
Yeah. So broadcast. Oops. All right. So you can see the slides, right? Yeah.
Yep.
All right. So I'm going to skip the high-level overview because you gave a nice summary as well. Thanks again for a good talk. So I will switch to, I guess, thoughts and questions. So, I mean, when I read the paper, at a high level, the result has a flavor of random coding arguments, but it's substantially weaker in some sense. So let me say the way I'm thinking of it. So random coding argument is also saying that, yes, you can find, if you basically, the code length is large enough, then you can find a code that will work. But it's actually saying something stronger, that any random code will be good. Mm-hmm. Whereas in the heart of what your proof is basically saying that with high probability there exists a subset that will work, or basically that's the kind of setup that you're operating in.
Yeah, so I think just a comment. So I think the way the correct analog would be to say any random network is good enough to prune, rather than saying that any pruning would be good enough. I don't know if that makes sense. So kind of like you start. So think of the pruning as the decoder, and think of the initial block as the code book, right? So not any decoder would work, in the same sense that not any pruning would work, but any random network could allow for good decoding, or I guess good pruning in this case. So I think that's the correct analog. Sure. Yeah. In the random coding thing, the algorithm is decoding algorithm is fixed, right? In some sense. Yep. Yep. Yeah. So I mean, so basically, what it's the same type of question. Stop screaming. Oh, sorry. No worries. Sorry about that. No problem. Cacophony. It will be extremely hard to find the subset from a computational complexity perspective. It's the same thing as in basically to decode a random code will be very hard. Yep. So around those, I had a few questions.
Oh, sorry, I have the cacophony is
not a problem. I totally understand.
So the optimization, yeah, working from home, working from
Yep, it has its challenges.
Yeah. So in some sense, in what some of the numerical results that you had used a mixed integer program.
Yep.
I mean, that would work for moderate sized networks, but otherwise as a solution is just as complex as training a large neural network. Or maybe
that even worse. Yeah, I agree. So in fact, so in our experiments, what we basically want to say is, whether the direct application of our theorems on the subset sum would yield something reasonable, and from the perspective of approximability, they do. But computationally, you should never, in fact, use the subset sum algorithm. In practice, what Ramanujan et al. Uses, they go beyond that, right? So they do use, it is the output, the decision variables or whatever are 0, 1, but the way that they get them is by continuous optimization, sort of, there's like a little bypassing thing that happens. So that is to say that you can avoid these issues. And I wholeheartedly agree that the subset sum approach is not the right way to do this. This is, I just want to stress out again that this is a tool to just prove the existence, but nobody should ever use it for pruning, at least in this form.
But I mean, I agree with that. I mean, that's what most of my comments are around, but I think that leads to some interesting questions. So maybe in the mixed integer program, there's some relaxation using some sort of SDP relaxation.
That's a great question. And I think kind of like, I would say even before going there, even if I had an exact solver for subset sum, which again, subset sum, it's only weakly NP hard, which means that, it is the complexity is polynomial in the input length and not logarithmic, which is what makes it NP hard. But still, I mean, in this case, if it's a bounded range of numbers, it's still polynomial. So it's not a big deal, I would say. The biggest issue is that our proof assumes the knowledge of what the target network is. In reality, you're only given access to the input-output pairs. And I think, the biggest question, even if you had, again, access to a solver for a subset sum, would be, how would you morph this theorem or this tool to be used with labeled pairs like X and Y's rather than the entire network? And I don't have a question, I don't have an answer to that, but I do think that it is worth thinking a little bit more about.
Sure. I mean, I guess you could assume in some sense that the original network, when you train it, it basically gives you zero training loss on the data, and then basically take that as a constraint in your pruning. Yeah, so then, I mean, all other things are more like for the problem that you're considering links, as you're saying, there is some analysis of the subset sum algorithm. So are there any approximation guarantees, as in basically, if I don't want the exact answer, can I actually get away with polynomial time? So
that's a great question. Yeah, and I guess one thing, and we sort of briefly discussed this before, but the over-parameterization plays a role here in how difficult the problem becomes. For example, in the result by Malek et al., the algorithm is very simple. You literally look, it's just like just a binary search. You go through the numbers, you pick the one that's closest to the original weight, right? So it's a much easier problem. And the reason why it's easier is because the network is really large. If you constrain it to be only logarithmically wider, then you stumble upon this wall of just requiring, at least in this case, the subset sum tool to prove something about it. So there has to be a relationship between computational complexity and the degree of over-parameterization, and to some extent the degree of approximation that I require. As you say, you may say, well, maybe to get epsilon is hard, but maybe getting epsilon times log 1 over epsilon is easier, right? So yeah, I don't have an answer to that, but I think this is a very valid question and a very good direction to think.
Yeah, and actually along the lines of what you mentioned, sort of bridging between what you have and Malak. Suppose I am willing to increase the width a little bit. Can I come up with saying that I can basically find a set of subsets? In some sense, they're asymptotically, the probability is going to be positive, right?
Yeah,
then basically I can use some sort of sampling procedures. I keep trying, and then eventually I will succeed. And so that's
that's a good point. So that's a good point. So in fact, so what I'm thinking here is, because those little diamond structures are the size of them, it's log 1 over epsilon, right? So you could say, you can think of this as almost a vector field. And if I wanted to have an epsilon on top of that somehow, like to take even every single subset, it's still log 1 over epsilon choose whatever. Right? So it's like 2 to the log 1 over epsilon whatever. So even if you want to look all of them, the complexity would be, I guess, 1 over epsilon. So in fact, you could do something like sampling from all possible subsets to approximate this problem. And the complexity would be, in fact, I think, a polynomial, precisely because you only have log 1 over epsilon of them.
Yes, that's correct. Yeah.
Yeah, that's a good point.
So anyway, those are all my questions. So thank you. I'll open it up now to broader questions.
Yeah, thanks so much. These were all really insightful and great questions.
Yeah. But anyway, thank you very much for a great talk. So let me at least thank you for that.
Yeah. Thank you so much. This was great. This was great.
It had a lot of discussions. So I think everyone enjoyed it.
Yeah, I really enjoyed the interactions. And if everybody who's still on the call, if you guys have any questions, I'm happy to take them. I can stay on the call for a couple more minutes.
I just have a question about the binary networks you're talking about.
Yep.
So what would be the benefit of ending with a binary network? Because I assume since you're pruning, it's going to stay binary the whole way. So like
that's correct. Yeah. So the benefit of binary. So that's a good question. So there's a lot of hardware benefits for having completely binary networks. In fact, if you could have binary networks and binary activations, that would be even better. But that may be a little harder to train. But the main benefit is the representational complexity, that you don't need the real numbers anymore, and also the finite precision, because in all the results that I described, there is this assumption that you have infinite precision. Once you convert to binary, you don't have to worry about this anymore, and you can prove finite precision results in this case. But then again, as I mentioned, it's the benefit of having an overall more hardware-friendly implementation or architecture. The other thing I want to mention is that in the Ramanujan paper, and these authors, the Ramanujan and Wartzman paper authors, they have a follow-up paper that basically said that the best initialization in terms of converging to a good solution is ±1, although they do require some weight. So they essentially realize every random weight as ±1 times some whatever amplitude, but everything is just like taking two values, and that seems to allow the algorithm to converge faster, which is, we still don't quite understand why this is the case. Like, you would think that, like, completely random numbers may be easier in terms of like allowing the algorithms to converge faster, but like binary allows faster convergence, and we don't really quite understand why.
Okay, thank you.
Yeah.
I have a follow-up question on the binary network. So I guess probably you want to tackle this from the theoretical perspective. But for example, do you know any empirical study about the lottery ticket hypothesis on binary network? Does it hold?
Yeah. So for the strong lottery ticket, the pruning only, there's nothing like for fully binary. There's nothing, to be honest. And this is something that my group, so my students are, some of them are experimental, some of them are on the theory side. The experimental folks have actually tried to train or prune, I should say, binary networks using the Ramanujan algorithm, that algorithm that maintains survival weights, and they were able to get close to the performance of like a full trained Reason 34, but not quite reach it. So it's still, we don't quite know how to do it right. So those pruning algorithms also tend to be unstable a little bit. So you change a little parameter, then they're completely, failing to convert. So the answer, I guess this is a long answer to your question. There hasn't been any work on the lottery ticket, either the strong lottery ticket or the vanilla lottery ticket hypothesis on binary networks, or at least I haven't seen any paper on it.
I see. So is this because it does not work, or actually I'm not sure.
Yeah, I don't know. I think it's probably because it's hard to converge. That people have been having. So we at this point we do have a theorem that says approximation-wise, it has the capacity. The binary network has the capacity to approximate whatever you want. So good solutions exist. How to find them? The algorithmic question is the difficult part. So we don't quite know how to get full performance out of those networks, like at least with the current algorithms that people are using. So I think it's an algorithmic question rather than whether, you know, there is enough capacity. There definitely is enough capacity in this case.
I see. Okay, thank you.
Yeah.
Are there any other questions from people? So I was thinking a little bit more, and I think, I mean, there is a better analogy to the random coding thing, because yeah, you're producing, your decoding algorithm is basically, I mean, maximum likelihood you could think of as looking through all possible code words and then checking which one is good. So it's something similar, all subsets in some sense, right?
Yep.
And so that algorithm is fixed, and then you're saying that you basically give me a random network, and that works in some sense. Any random network will work. So in that sense,
Yep.
the analogy is quite close.
Yep. But in fact, I guess, you know, you could come up with something, and this could be the way to improve the bound. So here, what we still do is we still do an approximation of weight by, so, you know, we have this diamond structure that's only log wider than the weight.
Yeah.
And we say, well, approximate weight by weight, right? But if you were to say, look, I look among all the subsets of n, you know, 2 to the number of weights of networks and find the best. So this would be the maximum likely decoder.
Yeah.
How good does that perform, right? And I think in that case, you probably need significantly less number of weights. I think that the proper dependence is like log, so inside the log, we have log depth, width divided by epsilon. The depth and width there, I don't think they're required. Like if you had a better,
needed, if you look at it in a bigger,
Exactly.
in the bigger sense of this case, yeah.
Exactly.
If there aren't any other questions, let's take Dimitri again. I think this was there were a lot of questions and discussion around this.
Thanks so much, folks. Yeah, this was great. I really enjoyed it. Thank you for inviting me, Vijay. And hopefully I'll be able to come to Ann Arbor once this craziness is over.
Yes, yeah, I hope so too. All right.
All right, folks. Have a great rest of your day.
Thank you. And happy birthday to your daughter.
Thank you so much. Thank you so much.
All right. Bye.
Thank you.
Bye-bye.